Hi, everyone. Thanks for having me here today. I'm going to be talking about our system EXO and sort of want to give you a bit, I come from academia, I'm supposed to inspire people more than build the software in some ways. So I want to convince you that we should be building power tools for performance engineers. So what do I mean by that? Well, if you're in the business of writing ultra-high performance code, you know that nothing beats trusty old assembly. It might take a while, but you can be sure it'll get the job done. Now, that's not to say you're a Luddite. Of course, you'll use fancy compilers, macros, templates, and any other cool new tool that'll help you work faster and smarter. Even so, there's a persistent myth that really fast languages, truly powerful tools, are powerful because they sacrifice safety. And I want to try to convince you that's just not true. As I've been illustrating here, modern woodworking power tools are chock full of safety features that empower the woodworker to move faster without fear of injury or producing poor quality results. In fact, safety is the overwhelming cost for hardware designers, who are the most performance-conscious engineers in the entire computing industry. So in particular, I want to tell you about a research compiler I've been building with colleagues at the University of Washington and MIT called EXO. EXO is designed to help performance engineers quickly and safely write peak efficiency subroutines. So let's start by unpacking that. A lot of, if not most of the highest performance code in hardware today can be found in machine learning systems. The architecture for these systems usually looks something like this. Using a stovepipe system design, models built from dense convolution and attention layers can reliably be targeted down to hand-tuned HPC code, running on custom accelerators like Google's TPUs, Apple's Neural Engine, or a number of the other accelerators we heard about just a second ago. One consequence of this system design is that the key portability interface is defined by HPC library APIs and not by the hardware ISA, as many people are used to. A second consequence is that all performance gains from accelerators are limited by the efficiency of this library code. However, there's little work on programming languages to help performance engineers who have to write these high-performance libraries. Okay, so what's so special about writing HPC libraries? Well, in usual programs, we expect user code to change rapidly as programmers develop software. Meanwhile, the hardware ISA changes very infrequently. In this system, the responsibility of targeting new hardware is put onto the compiler writers. The situation for HPC libraries is reversed. The specification of what programs should do, for example, BLOS or convolution, changes least frequently, even as hardware keeps getting updated. And even more frequently, performance engineers must constantly experiment with different ways of computing the same thing in order to find optimization opportunities. So the main approach in research, and in some parts of industry, has been to try to automate this optimization process. But full automation here would prevent performance engineers from doing their job, instead delegating it to compiler writers. Now, this sounds like a great thing if you're like a compiler writer, like many of you in the room are, I'm sure. But it's usually a losing cost-benefit proposition because even modest gains in efficiency can save millions of dollars at scale. That's what these performance engineers are being paid to do, after all. So to help performance engineers be more productive, we've been working on a new approach called EXO compilation, by which I mean a language and compiler design that externalizes parts of the compiler to give programmers more control. We call the particular EXO compiler we developed EXO. It's an imperative procedural array language, basically a subset of C. Here you can see a naive implementation of general matrix-matrix multiplication written in EXO. More specifically, EXO is a DSL embedded in Python that generates C code as output. That C code matches almost verbatim the Python embedded language. We do this rather than generating something like LLVM-IR because it enables us to support accelerators that rely on their own custom compiler toolchains. There are two basic ideas in EXO. We want to turn compiler backends into user libraries, and we want to put performance engineers back in control of making optimization choices. Okay, so what do I mean by externalizing this backend? Well, in a traditional compiler, as I was saying, including most domain-specific language compilers, the cost associated with targeting a new piece of hardware falls on the compiler writers as a consequence of the system architecture. But in EXO, this responsibility is externalized to users. This externalizing system decomposition is particularly necessary when hardware interfaces are proprietary and during the development of new hardware, since the ISA is unstable and frequently changing at this point. Okay, so what do I mean by user scheduling? Well, in EXO, we want to write this simple code I've been showing you, but end up with this optimized code. And we want to do that by supplying a supplemental metaprogram that we call a schedule that tells us how to transform one into the other. This idea, called user schedulable languages, became popular over the last decade as a way of writing high-performance code. Many of these systems treat scheduling as a way of parameterizing the lowering process, essentially additional input into my compiler, which lowers. Instead, EXO uses the less common, but I'd argue simpler idea of scheduling as rewriting within a single intermediate representation. Okay, let me go ahead and do a demo here. Now, this is going to be a pre-recorded video. Sorry, I can't type in space. I know that would be quite impressive. And I have to confess, I have a script. Is everything good? Okay, here we go. So in this demo, I'm going to target a matrix multiplication microkernel to run on the laptop CPU using the ARM Neon vector extension. Our goal will be able to achieve close to 100% of peak throughput on a single core. We're going to do this using the outer product approach, where we keep the accumulators for the C block resident in the register memory while we scan over the K dimension of the strips from matrices A and B. Now, you can see up there that the size for the buffers depends on an earlier argument. This enables our first safety feature, static out-of-bounds checks. EXO code is therefore guaranteed to be memory safe. Now, we start most schedules by renaming the procedure. Observe that rename here, like all scheduling operations, takes a procedure as its first input and returns a procedure as output. Our first code transformation is going to reorder the loops, moving the previously innermost K loop into the outer position. So let's go ahead and look there on the right. So we're printing out the before and after versions. And you can see the K loop starts on the inside and moves to the outside. Okay, we do this by specifying with a pattern match where we want to apply the scheduling operation. Okay, moving the K loop to the outside minimizes the lifetime of values loaded from the A and B buffers, consistent with our strategy. Okay, now let's go ahead and set up the accumulators for the C buffer. Rather than write directly into the C memory and DRAM, we're going to stage those values using the stage mem scheduling operation into a buffer that we're going to call C register. We say where to do that staging by specifying the find loop K, and then we say that we want to particularly stage the C buffer in the range 0 to 6 by 0 to 16. And you can see the results on the right there. Okay, in order to use this new intermediate buffer to model vector registers, we need to break the allocation up by the vector register width and change its memory type from DRAM to Neon, which you can see being done right here. Now, implementing these transforms by hand would have required us to write a lot of finicky index arithmetic code that EXO has generated for us automatically. Because indexing math is a common source of subtle bugs, automating its generation eliminates that large class of bugs. To make the resulting expressions more human readable, we can ask EXO to simplify them, and now that's a lot easier to see. Okay. Now note the memory staging created a load and store loop for transferring to and from those registers. Before we continue, let's target those loads and stores to the vector instruction set. To do that, we first need to divide up all of our length 16 loops by 4 to expose the vector width. We do that repeatedly, as you can see right there, modifying that scheduling operation. And we know that that division is, it divides it perfectly, so we specify that, and we won't get any loop epilogues. Okay, and then we can replace the innermost load and store loops with calls to the appropriate vector instructions using a kind of pattern match-based scheduling operation that we call replace. Okay, we've now got those instructions in there. Now, to stage the B buffer, it's going to be almost identical to the process we just went through for the C buffer. So I'm not going to bore you with those details. Instead, we can do one better. Let's abstract this process we just went through into its own reusable scheduling routine, which you can see here. If we look at the implementation of this new scheduling operation, we can see it's just a Python function that calls further scheduling operations. In fact, some of these operations now inspect the code. And this allows us to make decisions on what kinds of changes we should be making in response to what code happens to be passed in. And this allows us to generalize this code to new situations other than the one we originally wrote it for. But also note that unlike a compiler developer, we don't have to generalize too much. I, the performance engineer, am not obligated to ensure that my pass is correct for all possible code. Instead, I only need to devise a solution that works for my specific use cases. And in the interest of time, I'm going to go ahead and skip over the scheduling for the A buffer here. Okay. Finally, we're in a position to target the main computation into a vector fused multiply add. Let's go ahead and take that code that we just generated here. Here's the final form of it, and benchmark it. Now, interestingly, the original version of this code, as I was working on this demo, was targeting the wrong neon instruction, which resulted in the downstream C compiler using separate rather than fused multiply and add instructions. Okay, so what do I do about this? Well, in EXO, we can write our own instructions to extend the system. So in order to get that final factor of 2 of performance, I just extended EXO with this neon instruction. Instructions are just normal EXO procedures whose bodies tell EXO what the behavior is and how to replace it in for chunks of code. Then a string macro tells EXO how to generate the corresponding C code. It's a very simple mechanism which allowed me to extend the system in a matter of minutes with an otherwise missing instruction. Okay. That should be good. Switch back to the slides here. Okay. So I want to give you some performance numbers outside of this one case where, yeah, I got it up to 98% on my CPU, but okay, it's a microkernel for one size. So with less than a week of work, we were able to match MKL matrix multiplication performance on x86 with AVX 512 as our instruction set, achieving near peak machine throughput. We also got significant speedups on an open source ML accelerator from Berkeley named Gemini, as evaluated on a number of layers from ResNet 50. The results on convolution layers were similar. And compared to pre-existing code, EXO programs were an order of magnitude more concise. So I should mention 2 important limitations in EXO. First, we only allow linear indexing expressions. Nonlinear indexing is prohibited. And second, EXO currently does not support GPUs. I know that sounds crazy, but this is our current research focus at both universities right now. Handling GPUs is important for us because that's where the most performance-critical kernels run. By contrast, Triton is aimed at application-level programmers with computations important enough to port to GPU, but not so common that hardware vendors will invest time into optimizing them. Virtually all highly optimized code is metaprogrammed in one way or another. This spectrum of approaches ranges from absolutely no metaprogramming to writing your own compiler. At the simplest end, C preprocessor macros are a time-tested method for more productively developing specialized code. C++ template metaprogramming extends this idea with more structure. Libraries like NVIDIA's Cutlass BLOS take this strategy to an extreme. At the other end of the spectrum, projects like MLIR try to make the development of your own custom compiler a more tractable experience. We're mostly interested in this middle space, where we believe a bit more flexibility than macros and templates leads to significant simplifications. And as we explore this space, we're interested in how much programmability we can enable without turning performance engineers into compiler writers in the process. But maybe more importantly, user schedulable languages tend to be committed to a much higher standard of safety. And as I've said throughout this talk, power tools come equipped with safety features. Those safety features allow performance engineers to cognitively offload the problem of correctness to the compiler writer, just as the compiler writer offloads responsibility for performance optimization back to the performance engineer. This way, both engineers can spend more time focusing on their core competencies. You can find more information and resources about EXO at this QR link or at exo-lang.dev. Thanks for your attention, and I'll be waiting around afterwards if you want to chat with me in person.